why is text-to-speech synthesis important? Some basic stuff on how computers capture and store audio, the variety of different speech synthesis approaches that there are, grapheme to phoneme and what either of those words mean, signal processing that you might be using to manipulate speech to make it sound different, the flow of data from input text to synthesized waveform, how they're evaluated, and then some tools for if you wanted to make your own synthesizer from nothing. What do we use speech synthesis for? Obviously, there's things like GPS, where while you're driving a vehicle, you don't want to be taking your eyes off the road, so you can just use that audio channel instead of having a visual channel, though again, there's the visual channel that you can fall back on if you're not entirely sure from the instructions. Useful just generally as an assistive technology, so the visually impaired, dyslexic, illiterate or pre-literate to interact with textual data. So this is really important for certain governmental services which can't necessarily be handled by human staff, but if we put text-to-speech systems up so that they can interact with people, screen readers and that sort of thing, it's better able to address the needs of the public. Useful for people who are speech impaired, just general producing speech instead of them, automated announcements, second language acquisition, and then also research into speech perception disordered in a structured and methodologically sound way. So really basic stuff. What is sound? Sound's a longitudinal wave, so it's propagating through typically air when we're hearing stuff, but also basically any physical medium. We're often representing it as a waveform, so as you can see down the bottom, we've sort of got the longitudinal representation of what the sound wave actually is, but it's more convenient often to represent it as a transverse wave rather than a longitudinal wave, just because we can see that a lot clearer. In terms of the way that speakers and microphones actually work, normally we've got a coil around a magnet. There are lots of different ways of doing this, but this is sort of the most basic mechanism for capturing or producing audio. If you're capturing audio, that coil is attached to a membrane, which is then being displaced by some amount due to the incident sound wave. And then that's going to cause a corresponding electrical signal because it's in the presence of that permanent magnet. So a moving coil generates an electrical signal. That electrical signal will then get amplified, maybe a digital analog converter, to turn that into something that the computer can store in a digital format. And then if we're producing that sound back, we do digital to analog, analog to digital. So you sort of do that conversion the other way, and then instead of detecting from the signal that's in that coil, you're now driving that coil to produce a magnetic field, which displaces the membrane and therefore produces the sound. You may have seen these sorts of things on microphones, just generally speaking. They used to reduce the effect of directional airflow. So when you've got a membrane which is attached to this sort of coil, you only want it to be detecting the sound wave. If you've got things like wind, the membrane will be displaced because of the wind sort of pushing on that. So those can be from ambient sources, they can be from human plosives. So a plosive is, well, basically a p sound. So if you sort of put your hand in front of your mouth and you sort of go p, you'll be able to feel an exhalation of air on that. I'm just going to demonstrate the effect that this is having using this microphone. So this might be a bit loud. So this is sort of a omnidirectional damping mechanism. It's basically just a sponge. And the idea is when I am producing a plosive, if it isn't there, it's going to clip the microphone, it's going to fully displace the microphone membrane, and it's going to sound like this, which is not the best. Whereas if I then place something like this over the microphone and do exactly the same thing, it's greatly damped. Then I also have in my backpack this sort of thing, which is a directional pop filter rather than a wind filter. So using something like this instead, if you know the direction that the wind is going to be coming from, which you do if you're recording speech signals, it's typically a lot more effective than using a omnidirectional one. So yeah, when you see those big fuzzy boom mics when you're recording things out in the field, that's typically the purpose. The fuzziness on the surface of that is capturing crosswind and filtering it out mechanically rather than trying to do that digitally. And especially, again, if you're clipping it fully to that full displacement, that's not actually something that can be recovered using signal processing techniques. because there basically is no signal. The signal is going beyond what the capture system is capable of recording. So that can't be reconstructed later. You need to do this mechanically at the point of recording. Bunch of different recording types. So you've sort of got the omnidirectional mic when you're sort of wanting a whole soundscape. Directional mic is basically just recording sound along one particular axis, which is really useful for isolating particular audio sources. Again, this is the sort of thing that you want for speech. Lapel mics are useful because you can anchor them to clothing, and again, these might have filtering things so that if I lightly tap a lapel mic, it might be able to recognize that as something that's not part of the sound that it's wanting to capture. And again, there might be some DSP involved to filter that out, digital signal processing. And then similarly, head-mounted mics, which again are useful for isolating particular spoken instructions from a human operator. Again, basic stuff about the way that we're storing these digital signals. Things like sampling rate. So this is the basically the horizontal axis on this representation of a waveform. The idea would be when you have the analog sound, which is the smooth, continuous sinusoid there, we're sampling it at some particular frequency. The important thing here is that the, hands up if you know what the Nyquist sampling frequency of something is. All right, about half. Basically, the idea is if you're wanting to uniquely capture a audio signal, you need to be sampling it at least twice that frequency. So the idea is if you're capturing something at 8 kilohertz, the highest frequency that you will be able to represent using that is a 4 kilohertz wave. Now, the range of human hearing typically goes up to about 20 kilohertz, so this is why if you've ever listened to old audio files that you might have on really old machines, they'll typically sound really low quality. That's because they're usually stored at 8 kilohertz. That's enough for buzzers and whistles, but when you're listening to speech which has been recorded at that low sampling frequency, it sounds really bad. 44.1 is actually an interesting one. You might see 44.1 and it's like, that's a bit weird considering all of the others are sort of multiples of 2. 44.1 is actually an artifact of the fact that we have 60 and 50 hertz television frequencies. So the idea is that 44.1 kilohertz allows us to break down a full screen and then at either 60 hertz or 50 hertz, and then put an audio track on top of that. So 44.1 historically was very important for making sure that anyone would be able to play back that audio when you were going to be synchronizing it with a video track. And then 96 kilohertz, at that point in time, again by Nyquist, we're capturing really high frequency audio that's not necessarily something that you can hear, but what you are getting is the additional fidelity in the low frequency range, so you're able to say distinguish between two very similar frequencies, and you're able to reproduce that if you're using a higher sampling frequency. Bit depth, sort of your vertical axis and the fidelity that you have along there. 8, 16, 24, or 32 bits. After 24 bits, you're sort of at the signal-to-noise ratio that a human ear can't really tell the difference between the original sound and the reconstructed sound. So unless you're specifically trying to perform analysis on this, which if you're doing, say, wanting to identify abnormalities in the speech of someone, you'd want to be capturing at that particular depth just because you've got that additional detail. But in terms of playing it back for a listener, you never really care for more than 24 bits. And also lossless and lossy. So again, this is sort of MP3s versus WAV files. Obviously, MP3s, you can fit a lot more of them on your phone. The downside is when you're compressing them in this way, they might sound very similar to a human ear, but if you're wanting to do automated analysis or speech recognition or these sorts of things, the fact that they are compressed is often something which gets in the way of being able to actually recognize natural speech, because there are patterns in natural speech that are being removed by the compression that humans can't necessarily hear that the microphone's picking up anyway. This was originally a talk that I was giving to linguists rather than software engineers. I'm guessing everyone here is more or less familiar with compression by analogy. So if you're doing audio research, you always want to save as FLAC or WAV files. FLAC, you're getting a little bit of a benefit because that is lossless compression. But a lot of systems might not necessarily be able to import FLAC into them as easily as a WAV file. So if you're working with other disciplines, a WAV file is pretty much anyone's going to be able to open a WAV file in whatever weird programs that they're using. I'll just give an example of what it sounds like when we actually play back some of these. So this is a 320 kilobyte per second MP3 file. Very important cultural touchstone. But then if we go at a greater compression, you're sort of getting there's sort of acoustic glitches that you're picking up there, similar to sort of like the audio equivalent of JPEG compression artifacts. And then if we go all the way down to 8 kilobytes per second, it's basically, you know, substantially better quality because you can't understand that stupid song. So that's sort of why you don't want to be compressing things in a lossy way. And imagine trying to run signal processing on a signal that's been that heavily compressed. You're not necessarily able to get the useful things out of it. So in terms of speech synthesis versus text-to-speech, speech synthesis encompasses a whole bunch of different systems. So this is things like articulatory models for research. These are really detailed models of the vocal tract. So these are useful for studying things like dysphonia. So basically, if your vocal folds aren't working right, or you know, your ability to constrict certain parts of your vocal tract is reduced, let's say like certain muscles aren't working anymore, this is a way of analyzing the way that you might be able to compensate for that, say. Then things like phonetic input systems. So rather than inputting text, you're directly inputting the specific speech sounds or the configurations of the vocal tract that you want. Whereas text-to-speech, you're inputting you know, English language or you know, natural language text, and then wanting to go to a speech waveform. And there are specific challenges in that. Basically, you want to be able to pronounce any input word. So, you know, these are nonsense words. If we had a pronunciation dictionary, there'd be no corresponding pronunciation for tokens like blarp or frusel. But we might be able to look at those, and most of us would agree more or less on the way that those would be pronounced. And, you know, something like that nonsense of consonants there would also need a pronunciation if we're inputting into our system. So being able to break down input text into a phonetic representation. Distinguishing between what are known as heterophonic homographs, so basically hetero being different, phonic meaning sounds, so different sound, and then homograph, similarly same spelling. So basically words that are spelled identically, pronounced differently. So this would be like desert versus dessert, tear versus tear, bow versus bow. So these are things which can be determined from the context within the sentence, but if they're in isolation, there's, you know, no way for a human or a computer to figure out the way that it should be pronounced. And then things like choosing an appropriate intonation for a certain input sentence, things like prosody, which is basically all those components of speech that aren't just the phonetic content. So things like pitch, emphasis, volume, rate of speaking, all these different things. And then on a sort of higher level up, emotional content. So let's say that I'm saying something very sad. I wouldn't want to say that in a sort of happy-go-lucky voice. And this is something where a lot of text-to-speech systems don't necessarily perform this analysis. Like Google Assistant, if it's informing you a family member died, it's still going to be very upbeat about it. So that's, you know, a pretty major shortcoming when these systems are sort of entering into more and more of our lives. You want some level of tact in these systems. So what sort of approaches are there? This is one of the many fields which has been disrupted by deep learning recently. Historically, you've had concatenative approaches where you have a bunch of real-world recordings of an actual person talking. Often this is within very controlled conditions to make sure that that audio is pretty much perfect. No crosswind, no sound. This will be done in a lab. But you can, depending on the context, reconstruct concatenative banks from, let's say, speeches that someone might give. Often political figures are the easiest to get transcripts of. Then there are also parametric methods where rather than chopping up bits of real-world speech and rearranging them, you're using a dramatically simplified representation of the vocal tract and the vocal folds and all these different things, and you're using that to generate speech sounds. These are pretty good. They actually work a lot better for certain tonal languages, such as Chinese. Often you'll get concatenative systems will usually work better, except in these tonal languages. Then you have articulatory approaches, which are, again, more for research than necessarily systems that you'd implement and push out into the real world, just because they're very computationally intense. There you want as detailed a model of the vocal tract as possible, and again, these are used typically to analyze pathologies of the vocal tract. And then there are the two primary new machine learning techniques. There's tachotron, which basically goes from a sequence of text to a waveform, and then it's going directly from one to the other. So it's sort of folding in all of these intermediary steps together. And then there's WaveNet, which is doing a similar sort of thing, where you've got an input textual sequence, but then you are actually generating the waveform sample by sample, where tachotron is generating Fourier frames, which I'll explain what that is when I get to it. Concatenative approaches. So concatenate just means sequentially join. Everyone here probably is familiar with that term. You want to do things like smoothing the points that you're joining these particular sections of speech, because you can imagine if I had one waveform that was ending at a high position in the longitudinal representation, the transverse representation, and the other ones are low, you'll get an audible click as you transition between those discontinuities. So you want to smooth those. You also need to be able to manipulate the vocal characteristics. So because we're using pre-recorded sounds and we're reconstructing a waveform, we need to be able to say, I want to produce this at a different pitch, or I want to produce this at a different speed, but you also need to be able to vary those independently from one another. So there's a whole bunch of different signal processing techniques that you can use from that. But then the most important step in most of these systems is to go from the input text to a phonetic sequence. So I'll sort of give some definitions here. A grapheme is the smallest unit of a writing system. So basically, if we're writing in English, a grapheme would be something like A or B or C. A particular glyph or graph would be, some particular typeface or font representing the universal grapheme A. So a grapheme is sort of the set of all possible A's. Whereas a phoneme is very similar, but it's the same sort of thing for sound. So if I would say the words little versus little, you'd probably recognize that as the same word, but when I'm saying little as opposed to little, those are clearly two different sounds that I'm producing. So those would be two distinct phones, but they're phonemically serving the same purpose, because they're components of the same word that I'm producing. The International Phonetic Alphabet, if you've looked through a dictionary or on Wikipedia, it's basically loads of squiggles. Each of these corresponds to very specific articulatory configurations of the mouth and the vocal tract. Correspondingly, it's quite hard to type out IPA on traditional keyboards. There are some correspondences where basically using @ symbols and these sorts of things to more easily type out IPA transcriptions, but by and large it's pretty messy. What you often get is specialized transcription systems. So rather than having the very, very general IPA, which would be able to transcribe pretty much any language in the world, you can use a subset of it where you're defining your own symbols, which are easier to write, basically. And so that reduced phonetic inventory allows you to be, typing it out a lot easier. We don't need to consider all of these other weird squiggly bits that aren't important to us. ARPABET is probably the most common for English. It only has the relevant phones in it for American English, whereas there are phones in IPA like that sort of thing, glottal clicks and all sorts of stuff, which in English we don't really care to necessarily transcribe. And correspondingly, you can sort of see on the right-hand side there, they're a lot easier to write when you're just sitting in front of a QWERTY keyboard. Explicitly enumerating these rules is quite difficult, and this is obviously something where if we have letter to pronunciation correspondences, machine learning is really, really good at picking these sorts of things out. Hands up if you know what a sequence-to-sequence model is. Okay, a few people. I don't have too much detail on that, but sequence-to-sequence is a really common model for if you have an input sequence that you want to translate into a corresponding output sequence. So here we would have a machine learning model which is trained to take as an input some particular sequence of letters or glyphs in whatever language we're operating in, and output some particular sequence of phonemes, which is the correct way to pronounce that input phrase. And yeah, basically there's a bunch of different ways of aligning input letters to phones. Pretty much all of them work very similarly depending on the specifics of the machine learning algorithms that you're implementing. So, one-to-n versus one-to-one versus m-to-n. The m-to-n is what a lot of linguists will prefer when they're maybe inputting these correspondences, just because that's the most intuitive, whereas a one-to-n or a one-to-one alignment makes more sense for machine learning people, where it's like, okay, it's only ever going to be able to output one of these particular things. Like if we're doing a one-hot encoding or something like that, that's the representation that we need for it to be working in that way. As I said before, heterophonic homographs. Often these sorts of conflicts you can resolve pretty easily with a part of speech tagger. So you'd be able to run this on a sentence, and then hopefully it would throw out, okay, this particular word is a noun, this is a verb, this is an adjective. Getting these part of speech tags, and then hopefully would be able to say, okay, because this is being used as a verb, I know if I am bowing, then I'm not producing it as bowing. Whereas if I am tying a bow, there it's being used as a noun, and so we would be able to disambiguate in that way. But often that's not enough, so I've got a lead on the case versus I've got a lead brick. Their lead and lead are both being used as nouns within those sentences, and so part of speech taggers aren't always enough. Again, this is somewhere where throwing machine learning at the problem is normally a really useful way of tearing out these very similar things which traditional techniques were not particularly good at. So, in terms of concatenative synthesis, you might say, okay, just use one recording of each phone in the language. So it's like every vowel, every consonant, and then just cut them up and put them in order and play them back, and it sounds absolutely awful. You should really never do this. The main example that I could give would be in isolation, M, N, and which is sort of like the end of ing or something like that, so doing, are actually all acoustically identical in persistence. So you can go and n and ng, and then I can transition between all of them and you won't really hear much of a difference. Because it's all going through the nose, it's entirely nasal. So the configuration of the mouth, when in persistence, isn't actually changing the acoustic character of those. What's important is the transition to and from other sounds. So if I go ama versus ana versus anga, each of those, you can tell the difference because the prior and post vowels or consonants are changing the way that those transitions are occurring. So, and other things like vowel glides, so if I was to say fire, then that's a transition between f-a-i-a. Whereas if I was to say f-a-i-a, that's not going to be as intelligible as if I was to say smoothly fire as sort of a glide across those vowel sounds. So monophone synthesis systems are okay, but you would never use these in production. They're sort of like, okay, my dictionary is working, basically. I'm able to go from a dictionary to any sort of sound at all. So diphone synthesis is sort of the most basic, but still general system that you can implement. All you need is one recording of every phonetic transition in the language. That might sound simple, but in English there are something like 40 different phones, and then you have a transition matrix of 40 to 40, and then you're getting someone to sit down for a few hours and slowly record every single transition from one to the other, and they'll be very, very bored. But it does escape the problems of monophone synthesis because you can just concatenate these transitions instead of each phone in isolation, and it's pretty much the smallest database size that you can have. So a lot of really old systems would just be using a database of the relevant diphones to produce the audio that they would want, and it's not going to sound especially good. It will still sound pretty artificial because you will also get speech sounds interfering or affecting one another from more than just immediately before and immediately after. So things like triphthongs, which are basically combinations of three vowels, sort of a three-vowel glide, do not sound especially natural when you're using a diphone synthesis system. So you can go on to triphone synthesis, which unsurprisingly just means, okay, we've got phonetic context before and after each phone. So rather than just every transition from one phone to another, we've got every phone and every possible adjacency within the language. Here, we're sort of looking at 40 by 40 by 40. Conveniently, a lot of these triphones won't actually exist within the language that you're going to be synthesizing, so you can cross a lot of them out based on whether or not it's actually possible within that language to encounter that particular sequence of phones. This is kind of an intermediary choice where you don't need a much larger database, but you still find quite an improvement in terms of the quality of the sound produced by the synthesizer. Limited domain is a weird one where you want something really, really natural sounding, but you only want it to say sentences of a specific type. So anyone who's been on the trains around here has probably heard sentences of the phrase, sentences of the form, the train arriving on platform X in Y minutes, the Z train stopping all stations. So you might have someone read this sentence out, and then they will read out every number that is within the range of platforms. So they probably haven't recorded up to platform 99, they've probably only gone up to, what, 12, 18 maybe, at the biggest stations I can think of. And yeah, basically you only need to record those little bits, and then you're just throwing them in. Why would you want to do this rather than have a more general system? Because we don't care in these applications. We just want them to be really, really natural sounding. And if you are using, basically the larger the chunks of human speech you're using in concatenative synthesis, the more natural it is going to sound. Because it's those joining connections which are causing most of the abnormalities in the way that we're perceiving the sounds. But anything beyond a few different sentence types, it's not really useful at all. So unit selection synthesis is the most general form of concatenative, where we've got a big database of a bunch of different speech units of many different sizes. So there might be entire phrases like thank you or excuse me, where you're going to be using them very, very frequently. And so you're wanting samples of those entire phrases to maximize the naturalness when we're producing them. Often we have a bunch of different recordings for the same phones in these databases, so we have many different options to produce the same word. So if you're using a diphone or triphone database, you're pretty much going to be producing the same word exactly the same every single time. And while that might not matter if you're only interacting with it for a short period of time, if you're interacting with it for a long period of time, that's going to get very, very grating. So unit selection to some extent bypasses that, because if we want, we can vary up the way that we're producing those words by changing out the units with ones that we've got from elsewhere within our database. And again, because these recordings can be of any size, they're going to be more natural sounding. But then you have to, because there isn't sort of the one unit that you're using for each thing, you need to choose a target cost associated with each unit for how close it is to what you're actually wanting to be producing, and then a joint cost. So if two audio chunks don't actually sound very similar on the join, you're going to be penalizing that. Whereas two chunks which sound very similar in terms of the articulation at the point that you're joining them, that would be more beneficial, and so that would be a lower joint cost. And at that point you have a joint cost associated, you have a target cost associated, and then it's sort of a shortest path problem, essentially, at that point. So when we have these systems and we compile the waveform, we often want to then manipulate the pitch and the speaking rate. But the two are kind of intrinsically linked. So you're probably all familiar with, if you play a record, like one of the old vinyls, back at twice the speed, it's going to be a much higher pitch. And that's just because, if you have a sinusoid and then you're sort of squeezing it in time, that's going to be a higher frequency. If you're stretching it out in time, it's going to be at a lower frequency. So the two are intrinsically linked, unless you're doing some sort of intelligent algorithmic approach to change them independent of one another. Hands up if you know what a Fourier transform is. All right, that's most of you. More or less a way of taking an input wave, breaking it up into a bunch of sinusoids, and then representing their relative amplitudes to one another. So you can sort of see it visualized over there. We take the input wave, break it up into those, and then say, okay, this wave over this period of time is made up of these sinusoids added together. What we do with audio, though, is because we don't have a consistent wave like we might in other kinds of signal processing, we're actually interested in the frequency characteristics as they're changing over time. So what we use is the short-time Fourier transform, which is basically a sliding window across the speech waveform. Usually you've got some kind of a very simple window around it, usually a rectangular window, that you're then just moving across the speech waveform, you're getting the Fourier transform of everything within that window, and then you've basically got a bunch of bins, which you get the Fourier transform of, and then you can sort of see here the bottom, the vertical axis is corresponding to the frequencies which are being produced at each particular point in time in the waveform that's above. So you can sort of tell, you've sort of got these stripes along here at particular frequencies. Those are corresponding to the differences between different vowel sounds. So the difference between an R and an oo at the same pitch are what are known as formants. So basically these overtones that are combining together to tell us, even if I'm producing these sounds at the same pitch, we have peaks at different places within the spectral representation that allow us to perceive it as a different sound. MFCCs, mel frequency cepstral coefficients, they're very similar to the Fourier transform, except they're better representing the regions that humans are good at hearing. So basically, a standard Fourier transform would have loads and loads of bins in the high frequency range that, to human ears, we don't really care about. So MFCCs are often used for machine learning because they simplify a lot of what's important to human ears, or rather, they simplify the stuff that isn't important, and then they keep the stuff that is important. So it's better at emphasizing what humans want to have, retaining its quality. In terms of how people are actually making speech sounds, because I've gotten through this without really explaining that, under the assumption that this was originally a talk for linguists. So, three main acoustically important components to consider. So those are the vocal cords, or the vocal folds, which are vibrating at a particular frequency. You can sort of think of these as sort of pulsing open and producing bursts of air at some particular frequency. Then you've got turbulent airflow, which is produced by constriction. So if you're going like a s sound, because you're moving your lips together, it's constricting, and what you get is essentially turbulent flow instead of laminar flow because of that. And then vocal tract configuration, which is things like ah, oo, ee. We're not producing turbulent airflow, and they're all at the same pitch, but that's changing the resonance of the whole vocal tract. So everyone sort of, this will be a interactive bit. Take your hand, put it on your throat, and go ah. All right, so you should feel some vibration there, right? And that vibration is your vocal folds moving as each pulse is going through. So at a higher pitch, if I was going ah or at the lower pitch, it's going to be vibrating less, basically, or less frequently. At the higher pitch, it's going to be opening and closing much faster. Now everyone do exactly the same thing, but go s. No vibration. That's because rather than that sound being generated from the opening and closing of the vocal fold, it's being generated from the constriction that you're getting and the generation of turbulent flow. If we were to analyze that in terms of the Fourier representation, you'd basically have a bunch of wideband noise, because that's essentially what turbulent flow is. You're getting a whole bunch of different frequencies mixed together. But if you do exactly the same thing again and go zzz, it's actually a voiced s, right? So when you're producing each one, a s and a z are actually identical in configuration of the vocal tract, of the way that you're producing it. It's just that the z has that additional voicing. And then vocal tract configuration. So if I was to go ah, you, e, wah, you, things like that, right? They're all at the same pitch, but the formant frequencies that we'd have if we were looking at a frequency representation, each of those would have different peaks associated with them. So that's, by and large, at least in English, how we're producing most of our speech sounds. You can have unusual components like stops, or as I said before, clicks. So these would be things like t and k, where those are percussive components, but those can be represented in the same sort of way as wideband noise. It's essentially the same as hitting, say, a snare drum. It's going to be characterizable, and it's going to be basically just noisy within that region. Knowing that that's how speech is generated, there's a really computationally simple way of changing the duration and the pitch independent of one another. The component of voice which is actually producing the pitch is the vibration of the vocal folds. All of the rest of it doesn't really matter. And so you can think of it as each time I have a pulse of air coming out of my vocal folds, it's being acted upon by the resonance within my vocal tract, but it's still just a pulse. So what we can do is, if we move those pulses closer together in the time domain, we're increasing the pitch of the sound that's being produced, where all of those formant characteristics, the higher frequencies, are being retained within each pulse. And if we wanted to decrease the pitch, we would simply move them further away from one another. Normally, you algorithmically determine exactly where you wanted to put each of these pitch markers, and then you would just stretch them out or move them closer together. And because this is all being done in the time domain, there's no Fourier calculation at all. It's very, very computationally fast. So if you wanted to do this on an embedded system, it would just be, probably your best bet in terms of getting something that's going to sound decent. The alternative is to do a short-time Fourier transform, get your spectrogram representation of the whole thing, and then perform operations in that domain, like manipulating the fundamental pitches there, and then inverting it. The problem with inverting that is that it's not necessarily an invertible operation. So if we were to do something like this, so if the black line here is the original waveform, and then we're windowing it in some overlapping way, then we're performing some operations on it, and then we're coming back, then those windows might not necessarily be continuous at their join position. So there are a bunch of different ways of reconstructing it from a Fourier representation. The most common is Griffin-Lim, where basically you're ignoring the phase information of the Fourier frames, and you're just looking at the amplitude, and then you're trying to produce a waveform which roughly corresponds in terms of its amplitude to that spectrogram. So that's concatenative synthesis. Parametric is, unsurprisingly, using a parameterized model to generate a waveform from input text. The most common is a source filter model, which just models the vocal tract as a combination of audio sources and frequency filters. And this simplification makes it work reasonably quickly. And often these parameters will be trained using machine learning to match an existing speaker. So if we had a model which we had parameters that we could manipulate, and then we had audio from an actual speaker that we wanted to be matching, you can imagine some sort of adversarial approach where we're saying, okay, let's tweak this, let's tweak that, to try and mimic the output speech as closely as possible. And there are all sorts of different ways of saying, how far away are we in terms of how similar it sounds. Where you sort of need a distance metric, an acoustics distance metric between one speech sound and another speech sound. You can't sort of get the difference between the two waveforms because, a phase difference, where to a human it might sound identical. If we were to take the difference between those waveforms, it would be completely different. So this is sort of what you've got, your glottal excitation model, where your vocal folds are opening and closing and that sort of thing. This is very regular, this is very structured. It's pretty much just a pulse train. And then a frictional excitation model, which is, again, the sorts of fricatives, so things like s and sh, where it's all sort of wideband noise. Both of these are then added together, and then they're fed into a vocal tract transfer function. So this is sort of like the whole configuration of everything, and this is where your vowel character is coming into play. And then a radiation model. So just the fact that your lips are squishy, they're not completely rigid, is going to change the way that they're radiating out from your mouth. So I am sort of skipping over a lot of stuff here. There are a bunch of different more sophisticated models, but they are mostly quite similar to this. You also have, with a glottal excitation model like this, no need to worry about signal processing, because if I want to change the pitch, all I need to do is change the input train to my glottal excitation. I just need to generate a faster or slower combination of pulses, and I will have a higher or lower pitch corresponding to that. And similarly, if we want to produce slightly different fricatives, we can have some variation in terms of the frictional excitation model. And again, we can add some noise into these systems, so they won't necessarily sound completely robotic, but they will still sound quite robotic. I'll play some examples of parametric audio output later, just to demonstrate that. Articulatory is using a much more complex model of the vocal tract. So there are loads of different ways of doing this. There's sort of 3D models of the vocal tract. You might have a combination of tubes where it's a similar sort of thing as radiation coming out, but then again, the whole vocal tract is squishy to some extent. So that's something which needs to be physically modeled as well. Not really used in commercial systems. It's slow to compute, normally doesn't sound very human-like, but as I said before, useful for determining speech pathologies. Then we have tachotron, which I will escape out. Basically, what tachotron does is the same kind of sequence-to-sequence model of input text corresponding to audio output. What tachotron does is it goes from input text to a spectrogram, and then there is a transition from the spectrogram representation to a waveform. So rather than generating a waveform directly from the audio, it's generating these frames. We then do some reconstruction. That would be either Griffin limb reconstruction or, again, throw more machine learning at it and make it figure out how to reconstruct it effectively. And so, because it's trained on text, there are a lot of text tokenization things which it doesn't have to consider. So those examples where he has read the whole thing versus he reads books, because it's trained on a bunch of different input-output pairs, it figures out from context, sort of wholesale, okay, in this context, whenever I've seen it in this context before, I know this is the correct pronunciation output. So if we play this
back, he has read the whole thing.
Versus...
he reads books.
But you can sort of tell it's kind of a robotic sounding voice.
He reads books.
And then you also get some robustness to spelling errors. So if we were to do something like this in a concatenative system, we'd try and break each of those unusually spelled words down into a phonetic pronunciation. But here, because it's all, again, a input to output directly approach.
This is really awesome.
It's pretty robust to that. It also solves a lot of the problems with stress and intonation. Some of the problems that the original Tacotron had, though, are that you couldn't necessarily manipulate things like pitch at the point of generation. That's sort of fine because you can use the same sort of signal processing techniques and change it afterwards. And then this is sort of what you've got when you're just training a naive system versus their clever machine learning configuration.
Howard Quilly confirmed to All Hip Hop that he will be releasing an album in the next year.
But then there is also a pretty big post-processing step that's going on here. So before that post-processing step occurs, this is the output that you're getting.
Kojima Airport serves Toyooka.
So that's sort of very shaky in some sense, and that's because the reconstruction isn't particularly effective. But then they have a post-processing network that they're introducing to sort of smooth across that shakiness.
Kojima Airport serves Toyooka.
And produce something that sounds a lot better. So that's Tacotron. Thank you, Java. Then we have WaveNet, which sort of came out of left field because rather than generating Fourier frames, we're actually generating the waveform directly in the time domain. So this is trained on annotated audio signals. Reading the original paper, it's kind of opaque in terms of what they're doing because they don't necessarily explain what local conditioning they're training on in detail. But these are things like, here's what phone is being produced at this particular point in time across this particular region. And the original WaveNet gave really, really good results, but it was very, very slow. But recently they've come out with an updated version of WaveNet where it's operating in parallel. So basically, it's got a teacher-student network that is saying, okay, I want you to generate a bunch of data points simultaneously in parallel, given this particular sequence of random noise, essentially. So long as it's the same random noise that's being input, the same random noise waveform, it will produce coherent sounding output in parallel rather than sequentially. So sort of from this diagram, you can see it needs to generate the next sample before it can generate the following sample and so on and so forth. That was really slow. Now they've got it working much, much faster, but it still requires a fair bit of GPU, or I know that Google has WaveNet synthesis available on their cloud services, so they're probably doing something with TPUs there as well. So in terms of evaluating whether or not a text-to-speech system actually works, if we're in pretty much any other field, it's just, okay, in mathematics or engineering, we just say, okay, does the bridge break or not? How fast does the algorithm work? When we're talking about text-to-speech systems, we need to say, okay, how good does it sound? So we will usually break this up into two different categories. There's intelligibility, which is how well someone can understand the words that are being said, and then there's naturalness, which is either how natural or how human-like the speech of the system sounds to a user. Naturalness isn't necessarily human-like. Like, you can have a very natural-sounding robotic voice, which clearly isn't human, but it still sounds coherent and not sort of janky in the way that you might get from a more basic system. But both of these need to be evaluated with a human in the loop. You need a human to say, okay, did you understand that particular sentence or not? Normally that's through transcribing some particular textual input that's been synthesized, and that's a bit more objective in terms of either you heard the word correctly and transcribed it correctly, or you didn't. But naturalness needs to be evaluated subjectively, and that's typically on a 5 or 7 point scale, which we then aggregate over a bunch of different people. This is something where most researchers will throw something up on Mechanical Turk. And then you have these standardized sentence lists. So the Harvard psychoacoustic sentences, just 72 lists of 10 sentences. They're all phonetically balanced. So the particular phones that are being used are roughly the same as would be used in the English language on a larger scale. And they're also semantically meaningful. So what that means is if, say, one particular word in any of these sentences was produced really badly, usually human listeners will be able to fill in that gap by the fact that, okay, whitings are small, blank, caught in nets. It's like, okay, if I know a whiting is a fish, I probably know, even if it mangles the word fish, it's probably fish. So these sentences are tolerant to corruption in that way. The main alternative to that is the Haskins sentences, where they are phonetically balanced in the same way, but they're all semantically meaningless. So you get phrases like the black top ran the spring. And while that might be grammatically correct, syntactically correct, like that seems to be a syntactically valid sentence, that doesn't mean anything. That doesn't necessarily evoke an actual real world image. And so due to that unpredictability, it usually gives a greater error rate in terms of when people are trying to listen to and transcribe those sentences. And so basically, if you have a bunch of systems which are maxing out in terms of the intelligibility on the Harvard sentences, you might throw in the Haskins sentences where, because they're basically absolute nonsense sentences, everyone is expecting people to perform far worse with those examples. Some of the interesting things going on in the field at the moment are things like one-shot learning. So with low-resource languages, especially with, for example, Indigenous Australian languages, we would be really lucky for a lot of these to have anything more than 20 or 30 minutes of transcribed audio data for the entire language. And that's normally one speaker. So it can be really, really difficult to get these sort of systems working and out in the field for them. So what will often happen is that you have a pre-trained system which is able to synthesize speech in a similar language, and then you could do some transfer learning across to the similar language. So if the phonetic structure of the language is very similar to another language, you can often actually just use that synthesizer as is, because if they're, the words which are being spelled phonetically might be, absolute nonsense in one language, but the sounds that were being produced are intelligible in the other. The two synthesizers can be used interchangeably, so long as they share that same writing system. And it typically works better for languages which have a very regular phonetic inventory, or a correspondence between the speech sounds and the transcription of it. So English is a really bad example of this because the spelling and structure of English is really chaotic and chimeric. Whereas languages such as Japanese or Korean, where they have a very modular phonetic inventory, where you will typically have like vowels, or each vowel has one particular consonant associated with it. You won't get things like vowel glides and consonant clusters in the same way. So one-shot learning will often work better for languages which have those kinds of structures. And again, in terms of the way that you're representing visually these sorts of systems, it can be really, really simple, or it can be really, really complex. With the one on the right, there's a lot of things that I've skimmed over. So for example, tokenization. So you might want, for example, to be able to pronounce any input number. So if we represent some particular string of digits, you want to be able to pronounce that string of digits, but then you might want to say, okay, is this string of digits a phone number? Is this string of digits a really big number? Is it a digit sequence? So being able to tell which particular one is appropriate is, again, often a machine learning problem. There are some simpler ways of doing it. If you're sort of saying, okay, always assume it's a number, that's 3,487,000 or something. But if you're reading that out when it's a phone number, that's not useful for the person who's trying to write down all the digits associated with it in a string. There are also things like particular stresses within words. So emphasis on certain syllables, for example. and even syllabalization as opposed to just phonetic inventory. So things like hello as opposed to hello, as sort of like a smoothed, smeared out sort of thing. So I'll just go over a few tools that are available if you wanted to implement some of these sorts of things. Pitch shifting is, as I said before, this sort of the time domain p-solo way of doing things. The two main vocoders that get used for research are Straight and World. They both come out of a research group in Japan. Straight, you have to sign an agreement to get access to it, but World is fully open source and available to anyone. So if you're interested in doing that sort of thing, that's really easy to do. Audacity also has some basic pitch and duration shifting available, but that's not a speech-specific algorithm. So World and Straight are designed around the assumption that the signals that you're putting in are speech signals as opposed to generic sound. So Audacity works really well for generic sound, but when you're doing this specifically for speech, it's not necessarily going to work as well, and the output's not going to sound as natural. Grapheme to phoneme training, there's, again, sequence-to-sequence models available. You're pretty much just training on a collection of word pronunciation pairs, so pronunciation dictionary. There's a bunch of different machine-readable pronunciation dictionaries. The most available and easiest to use would probably be CMU Dict, which is Carnegie Mellon University Pronunciation Dictionary, where you have input words and pronunciations in American Common English, basically. So you'll have received R's in most words, but it still remains intelligible. And then there's gentle. So gentle, if you're wanting to do anything more sophisticated than a triphone, is really, really useful. So basically, if you have audio and a corresponding English language transcription, gentle will get you an alignment between the two. So I can show an example of, have the examples of the different kinds of synthesizers. So in English, when we have a concatenative synthesizer, it will sound something like this.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
So all of the components of that, if you were to listen to them in isolation, will sound quite natural. The reason that it might not sound as natural as it could is because we're joining all of these components together. If we listen to a parametric synthesized speech.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
So that kind of sounds robotic, and the reason for that is because the glottal excitation model is very, very regular. So because we're not using sort of the human element of randomness in terms of the way that the glottal pulses are occurring, we don't have that variation that you'd want. And here is a WaveNet output corresponding to those two.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
So it's sort of a few steps above the parametric approach. It doesn't really have the join problems that concatenative approaches do, but again, it is very intensive to get an output with at the moment. And I can give some kind of indication in Mandarin Chinese as well as to why parametric might be a little better than concatenative.
一般商业航班在1919年来往于美国和加拿大。
I don't speak Mandarin Chinese myself, but I get told that that is far more intelligible than the concatenative approach, where
一般商业航班在1919年来往于美国和加拿大。
where you can sort of tell those join costs are, in a language like English, it's not as important, but in a tonal language that has a dramatic effect on the naturalness of the output. So going into what I was talking about with gentle, I'll just sort of demonstrate what the output you're essentially getting.
Force aligners are computer programs that take media files and their transcripts and return extremely precise timing information.
So basically, you input audio, you input an associated transcript, it will get alphabet pronunciations using CMU Dict, and then it will get an alignment between the two. As part of this, it will actually downsample to 8 kilohertz, which does not sound the best, but you can then say, okay, I'm going to listen to the original wave file, and I'm going to concatenate it at that higher sampling rate. So it will sound a lot better when we compose it in that way. And then, yeah, there's the CMU pronunciation dictionary, where if we have some particular sequence of words, we can just sort of look it up. And it's sort of human readable in a way that the IPA isn't necessarily as immediately intelligible to someone who isn't a linguist. So you can sort of say CMU dictionary, which CMU dictionary. And so yeah, this is just a big database of all of these English word to phonetic pronunciation correspondences. Okay, so there are a few different approaches. There's it's normally sounding robotic because, not necessarily because the input audio isn't being emoted correctly, but because we don't necessarily know what emotion we should have associated with the output. For example, with a text-to-speech system such as Siri or Google Assistant, the objective there isn't necessarily to have an emotive or a natural sounding voice. It's really important just to get it intelligible. A good example of this is, for example, Stephen Hawking's synthesizer. So it doesn't sound especially natural, but it is extremely intelligible. And one of the advantages of that is that you can actually play it back much faster and still be able to understand what someone's saying, or what the synthesizer is saying, at a much faster speed, but it still sounds very robotic. So it's more a case of those kinds of contexts need an additional layer on top, which at the moment most systems aren't really interested in. Most people don't need a emotive Google Assistant or an emotive Siri when they're just getting directions to a car or something. Often there are markup languages where you can input particular pitches and durations on the phonetic level for a lot of different synthesizers. I know that Google supports this now. They didn't until the more recent Android versions, but now you can just input using a standard markup for, okay, I want this pitch to be produced for this amount of time in this particular phone. And if you're wanting to go in on that low level, you can produce whatever contour that you want. The downside is it won't do that automatically for you. I think Amazon has some interesting stuff in terms of emotional speech synthesis. Again, this is something where even categorizing emotions is an open question, right? Because it's a very fuzzy category. It's like even enumerating the emotions is something where there are researchers in the humanities who have spent their entire lives trying to do it, and it's it's like, okay, is it 50 or 100 or whatever? There's a prominent researcher, Ekman, I think, who did a lot of work on facial microexpressions, and so he's sort of categorized a whole bunch of different emotions. There's also some stuff with machine learning where there have been a bunch of different utterances which they embed into a high-dimensional space, and then they see where you have kind of continuities between different emotions. So yeah, it's a very underspecified problem at the moment, and you do need an appropriately increased amount of training data to be able to say, this is what sad sounds like, this is what happy sounds like, this is what scared sounds like. And then it's like, okay, how do we additively combine happy and sad? Is that something that it even makes sense to do? And then what does that correspond to? It's really not something which has been formalized enough for people to just throw machine learning at it at the moment. Though if you had enough training data, and this is where you want orders of magnitude more training data than even people like Google have, then it's possible. And again, I think Amazon has something like this at the moment. But certainly in terms of intelligibility and intonation, it sounds pretty natural, especially compared to systems even 5 or 10 years ago. So when I was saying that they don't necessarily sound emotive, that was specifically with regards to the prosodic contours. Absolutely. If we get you with your consent and you sat down and you recorded voices in a lab setting, absolutely would be able to do that. You can also do this, and I've done this, and this is widely known political figures like Donald Trump, where it's like they give speeches, and those are under very controlled speaking conditions, and so you're able to make concatenative databases from all of their chunks of words and stuff. But you will run into the same sorts of problems as I was saying before. It might not necessarily sound emotional. It won't be the way that that actual human would be producing it, unless you have loads and loads of training data. But you could certainly generate something like that. And again, the starting point for something like that would be getting an alignment with gentle from training data. It can work for a concatenative approach with even as little as 10 minutes. But the problem is that if you, say, don't have a particular phone or a phonetic sequence in that recording, then you've got to compose it out of the smaller units and it's going to sound less natural. So, as with all things, more data is better in terms of the effectiveness of the thing. As I was saying, Japanese and Korean and other languages with very modular inventories, because there are very obvious beats to the language in some sense. It's like you've got ka and ga and all of these consonants associated with one vowel, and it's very obvious where the stress within a word should be placed. So in some sense, it is easier to learn those kinds of languages than it would be for something like English, where the emphasis within one word could be in a bunch of different places, and the meaning could be changed dependent on all of that. So in some sense, at least for Japanese, I know, and again, this is why there's so many really good speech technology researchers in Japan, because a lot of these problems in the Japanese language have been solved, and have been solved for quite a while. Have had effective solutions available for quite a while. And so they've been working on the higher level problems, such as, okay, how do we get emotive speech and those sorts of things. And I mean, generally, because of things like that, you've got virtual singers like Hatsune Miku or whatever, where you've got, okay, because you have that modular inventory, I just say, I want a ga at this particular pitch, I want a ka at this particular pitch. And it can do that in a way that, because of the glides across vowels and consonant clusters and weirdnesses that you get in other languages, but basically those languages don't play as nice. So yeah, I don't want to say it's an easier problem. Certainly there are different problems in that, but in particular, it's a few steps ahead just because the structure of their language is such that they kind of have a head start, as opposed to something like English. So what normally happens is there's a special interest group on speech synthesis specifically, and there's something called the Blizzard Speech Synthesis Challenge, where you have a bunch of different research groups, and then a specific data set is made available to everyone, and they say, okay, here is all of this aligned data, maybe in English, maybe in a language that none of the people entering even understand. And then it's, okay, here is this data, make the best synthesizer that you can. Everyone designs their system. Again, the training set versus the test output is kept separate, as it should be. And then it gets evaluated by a large group of people. So there's the experts within speech synthesis within that field. So they will often be harsher on certain things because they've kind of got an ear for certain things. So it's like picking up on certain elements of roboticness, where a casual listener wouldn't necessarily pick up on that. That, or often throwing it on Mechanical Turk is a pretty good option. The idea is more, not necessarily as an objective score, but more as an aggregate relatively. So the idea is, if one synthesizer is much better than another synthesizer, you'd expect that number on a given population would be higher. So it's not necessarily, I tested this and it got a 4, and this other one, which was tested under completely different circumstances, got a 3, so mine is better. You need that particular population to evaluate a bunch of different things at the same time under the same conditions, and then the idea being, if there's some sort of order-preserving way of combining all of these things, then you should be able to say, okay, this one is in a lot of ways better than this one, as aggregated across it. But it is a very subjective thing. That is how it's normally done. So you wouldn't sort of present, okay, here is one score in isolation. You would run that score at the same time as a bunch of other scores. So when they're running the test on WaveNet, like they've got their concatenative parametric WaveNet and also the human speech baseline, right? So in an ideal world, human speech would be full 5s on everything, but you know, there are some people who don't think that natural human speech is perfectly natural just because it's being generated by a computer or something. So human speech, again, depends on the language. In English, you're normally hovering around 4.5, and you can see WaveNet was a huge step up in terms of the naturalness of speech synthesis. So the idea is the closer that you're getting to human speech, and there are quite a lot of tests where they're performed better than human speech, but that's probably because the human speech has been sampled at a really low sampling rate. And so the human speech, when they're playing it back, just sounds like garbage because the file is, it's not an equal playing field in that sense. So yeah, it's more of a relative thing than an absolute thing.